Welcome. In this FinDaS explainer, we're going to dive right into the core tech that powers the entire crypto economic world. We'll cover the basic architecture, the rules that govern it, the security that locks it down, and finally, how we actually interact with it using wallets. By the end of this, you're going to have a really solid grasp on how this whole thing works.
So here's how we're going to break it down. First up, what even is a blockchain? Then we'll get into how these huge networks all agree on things. That's consensus. After that, we'll look at the cryptography, the stuff that actually makes it secure. And to wrap it all up, we'll talk about wallets and what it really means to own something digitally.
Okay, so let's get right to it and start with the most fundamental piece of the puzzle. What exactly is a blockchain?
So at its core, you can think of a blockchain as just a shared digital record book, a ledger. But, and this is the key part, instead of one single person or company controlling that book, everyone on the network has a copy. See, new transactions get grouped together into these things called blocks, and then each new block is cryptographically chained to the one right before it. This creates this permanent, unbreakable chain. And that structure, well, that's what gives blockchain its two superpowers: transparency, because everyone can see it, and immutability, which means it's basically impossible to change.
Okay, so how does a transaction actually get on the chain? Well, it's this really cool 6-step process that all happens out in the open. First, you, the user, submit a transaction. Then, someone on the network, we call them a node, grabs your transaction and a bunch of others and puts them into a new block. That block then gets broadcast to the whole network for everyone to see. And this is where the magic happens. All the other nodes check the work. They make sure everything is legit and no rules are broken. If it all checks out, the block gets added to the chain and the node that did the work gets a little reward. And boom, your transaction is now a permanent part of the record.
This image here really helps visualize that whole flow. Look, right there in the middle, see how the block gets sent out and validated by all those different nodes? That is the most important part. It's a system of checks and balances, but it's done by the whole community, not some central company. And this idea of distributed trust is what makes things like banks or clearinghouses totally unnecessary. You're not trusting a company anymore, you're trusting the math. Now, this straight line of blocks is the classic blockchain design, for sure, but it's not the only game in town. Some systems use something totally different called a directed acyclic graph, or DAG. So instead of a single file line, imagine a tangled web where new transactions are constantly confirming older ones. It's just a different way to tackle the same problems like speed and scale. We're not going to go too deep into it today, but it's just good to know that innovation in this space goes way beyond that original blockchain idea.
All right, so we've got the structure down, but hang on a second. If you have thousands of computers all over the world run by people who have never met, how in the world do they agree on what's true, right? That is the huge challenge here, and it's solved by something called consensus.
Here's a good analogy. Imagine a huge board game being played all over the world, and everyone is keeping score. Every single player has their own notebook, and they write down every move. Now, before anyone can make the next move, everyone has to check their notes and agree that the last move was totally valid. If someone tries to cheat, their notebook won't match up with anyone else's and the whole group just says, nope, not valid. That's basically consensus. It's how you get everyone to agree and stop fraud without needing a referee.
So the two big ways networks do this are called proof of work and proof of stake. Proof of work, which is what Bitcoin uses, is basically a huge computer race. Miners use tons of computing power to solve a really hard math puzzle. The first one to solve it gets to add the next block. This whole thing is secured by how much energy and hardware it takes. It's just too expensive for someone to cheat. Now, proof of stake is different. Instead of a race, validators lock up their own crypto as collateral. That's their stake. If they play by the rules, they get rewarded, but if they try to cheat, the network can actually take away or slash their stake. So this one is all about economic security. You have skin in the game, so you're incentivized to be honest.
This whole field of study is actually called cryptoeconomics. And the main idea is actually pretty simple, but it's super powerful. You want to design a system where it's just way more profitable for people to cooperate than to attack the network. You see it with the rewards for miners and validators, right? You also see it in newer stuff like DeFi, Decentralized finance, where people get rewarded for providing liquidity. The entire system is built on these really smart economic incentives that keep everything secure and running smoothly.
And a perfect example of this is the Bitcoin halving. Basically, the reward for creating a new block gets cut in half about every 4 years. It went from 50 Bitcoin down to 25, then 12.5, and it just keeps going. What's amazing is that this isn't some decision made by a group of people in a boardroom. It's literally written into the code. It's like an automated monetary policy. It creates the super predictable, transparent supply of new coins that everyone has known about since the very beginning.
Okay, so how is all of this, the security, the immutability, the consensus, how is it all enforced? Well, the answer isn't about trusting people or organizations. It's all about the cold, hard math of cryptography.
Let's start with a really basic tool called hashing. And honestly, the meat grinder analogy is perfect. You can shove any kind of data into a hash function. I mean anything. A single word, a huge document, even a movie. And out comes this unique, fixed-size digital fingerprint. We call it a hash. But here's the magic part. It only works one way. You absolutely cannot take that fingerprint and work backward to figure out what the original data was. And that one-way trick is exactly how we link all the blocks together so securely.
So, for a hash function to be truly secure, it needs 4 things. First, it has to be deterministic. That just means the same input will always produce the exact same output. Super important for verifying things. Second, it has to be one way, which we just talked about. You can't reverse it. Third, it produces a fixed-length output, which is great for keeping things neat and tidy. And finally, and this is maybe the most important one, it has to be incredibly unpredictable. If you change just one tiny thing in the input, like one letter in a book, the output hash becomes completely different. This is called the avalanche effect, and it's what makes it so obvious if someone tries to tamper with any of the data on the chain.
Now, the other big piece of the puzzle here is encryption. And the real game changer for these networks is something called an asymmetric key pair. So forget about having one shared password. With this, you get 2 keys that are different but mathematically connected. You've got your public key, which is kind of like your home address or your email. You can give it to anyone. That's how people send stuff to you. But then you have your private key. This is your secret. It's like your password, and it's what you use to prove you have the right to send assets from your account. This whole public-private key system is, without a doubt, the foundation of digital ownership.
And that whole idea of public and private keys leads us perfectly into our last topic, wallets. So how do we actually use these keys to do stuff on the network and manage our assets?
This actually brings up a really important question. And to be honest, it's probably one of the biggest misconceptions out there. We call it a wallet, right? So you'd think it holds your crypto, just like your physical wallet holds cash. But is that really what's happening?
Okay, if you remember one thing from this whole session, let it be this. Your wallet does not hold your coins. It doesn't. Your assets, your crypto, all of it. It all lives on the blockchain, always. Your wallet holds just one thing, your private key. And that key is what lets you sign transactions, which is basically you proving to the network that you're allowed to move those assets. So you see, a crypto wallet isn't so much a wallet as it is a keychain.
So since your keys are your assets, protecting them is literally everything. In this space, you are your own bank, and that means you also have to be your own security guard. This means you gotta follow some strict rules. Use hardware wallets to keep your keys offline. Make secure backups of your seed phrase and keep them offline too. And never, ever share your private key with anyone. For really valuable stuff, you can even set up what's called multisig, which requires multiple keys to approve a single transaction.
So where do all these keys come from anyway? Well, it all starts from your seed phrase, or as it's sometimes called, your recovery phrase. That list of 12 or 24 words, that's the master key to everything. From that one phrase, your wallet can generate all the private keys and public addresses you'll ever need. It makes it super easy to recover your wallet if you need to. But it also means that phrase is unbelievably important. You have to protect it like your life depends on it. Because if someone gets a hold of your seed phrase, they get a hold of everything you own. All right, let's just quickly recap. We've really built this from the ground up, haven't we? We started with the basic structure of the blockchain. Then we talked about the consensus rules that keep everyone in agreement. Then we layered on the cryptography that makes it all secure. And finally, we looked at the wallets that let us actually control our stuff.
So I'll leave you with a question to think about as you move forward. Which of these consensus mechanisms is actually the best one? The honest answer is, there isn't one. It's always a series of trade-offs. What are you trying to optimize for? Is it pure security? Is it speed? Is it energy use? Or is it maximum decentralization? Figuring out how different projects answer that question is really the key to understanding this entire space. Thanks for joining me. If you're ready to go from theory to practice and apply this blueprint to your own project, please visit us at FinDaS.org. We have more in-depth materials and token design support waiting for you.